How has the climate of Antarctica changed in the past? Is global warming having an impact on Antarctica, and how may its temperature alter in the future? What proof is required to answer these queries? The issue of human-caused climate change, also known as global warming, is now well known. Our use of fossil fuels, such as coal, oil, and natural gas, as well as agricultural practices, have increased the concentrations of greenhouse gases in the atmosphere, particularly carbon dioxide and methane, which are now significantly higher than pre-industrial levels. The atmosphere warms as a result of more heat energy from the Earth's surface being trapped in the atmosphere rather than escaping to space as greenhouse gases build up. The complexity of the global warming issue, such as the amount, rate, and pattern of warming, is largely due to our inability to fully comprehend the ripple effects that the increase in greenhouse gases will have on other aspects of the climate system. Of course, greenhouse gases are not the only factor influencing the Earth's climate. On a variety of timescales, there are also natural variations in the climate, as well as both natural and man-made variations in how the greenhouse gases themselves cycle between the atmosphere, land, and oceans. In conclusion, it takes far more effort than it might seem at first to comprehend and anticipate climate change. This project has benefited greatly from research on Antarctica, particularly from examinations of Antarctic ice cores. The ice cores have made it possible for scientists to reconstruct historical climatic variations spanning hundreds of thousands of years, as will be discussed further below. We now have a much better understanding of past climate variations due to natural causes than we had in the past, and this has given us important context for evaluating more recent human-caused changes. The polar regions are frequently referred to as the canary in the coal mine for detecting global warming, and some of the research stations covered in regional climate variation and weather offer crucial weather information for determining how the polar regions will react to the increase in greenhouse gases. Additionally, since Antarctica is home to 90% of the world's ice, what happens there will have a significant impact on the rest of the world. Evidence of past climatic change in Antarctica is found in the ice. The climate that exists today didn't always exist in Antarctica. Fossils show that at various points during the continent's geological history, trees were present and covered much of Antarctica when it was much warmer. Many millions of years ago, differing geological structures and ocean circulation patterns led to these warm periods for Antarctica. See the main causes of Antarctica's temperature. The majority of the continent has been blanketed under ice for at least the last 6 million years. The ice core record goes back to roughly 800,000 years ago, in contrast to the much older geological data. Since the distribution of land and sea has mostly remained constant over this period, the variations in Antarctic ice provide more insight into how the climate fluctuates under the current tectonic arrangement and how it might alter in the near future. Drilling into a glacier or ice sheet and removing cylinder-shaped chunks of ice produce ice cores. These ice chunks are the result of thousands of years of snow accumulation. Each year's snowfall buries earlier snow layers, which later become compacted into glacier ice. An ice core's layers are made of snow that fell at specific points in the past, and each layer acts as a time capsule by recording information about the weather at those points. The appeal of ice cores is their ability to provide us with a wealth of information about historical climatic and environmental conditions. Additionally, the evidence is constant over time and has a high degree of accuracy when it comes to dating. Among the most significant sorts of proof and data are: the air temperature at the time the snow fell is reconstructed using the stable isotope ratios of the oxygen and hydrogen that make up layers of ice. Where annual layers of ice may be seen, the thickness of the layers reveals the historical annual snowfall totals. The amount of dust that has been retained in ice layers provides evidence of how much wind erosion has historically occurred on continents, related to both the strength of winds and the levels of vegetation cover over the land in the past. Tephra fragments and the acidity of the ice provide evidence of past large volcanic eruptions. By measuring the carbon dioxide and methane levels in the trapped air, it is possible to determine how these greenhouse gases have changed over time in the atmosphere. The fundamental principle underlying the interpretation of stable isotopes in ice cores is that the heavier isotopes of hydrogen and oxygen will condense out more readily than the lighter isotopes as air cools and condensation occurs. As a result, when precipitation happens, the water added to the ice sheet is light since the heavier isotopes of water vapor will be more depleted the colder the air gets, e.g. the ratios of 18O to 16O and 2H to 1H will be less. On the other hand, the proportion of heavy to light isotopes will rise as the atmosphere over the ice sheet warms. These ratios are calculated in proportion to standard mean ocean water, and they are stated as per mil rather than per percent. SMOW. The isotope ratios of water vapor in the atmosphere, and consequently precipitation reaching an ice sheet, are always negative in respect to SMOW because H2O with the lighter isotopes evaporates more readily from the ocean. As an illustration, the oxygen isotope ratios from the Byrd ice core in West Antarctica range from -33 to -43. The Byrd ice core exhibits temperature changes on the order of 15 degrees Celsius during the previous 100,000 years, since there is a shift of around 0.70/00 for every 1 degree Celsius change in the mean annual air temperature. Around the world, ice and glacier cores have been taken from several glaciers and ice sheets. Since Greenland experiences higher snow accumulation rates than Antarctica, much of the pioneering study was conducted there, and the Greenland ice cores offer a more precise record of change, with annual layer counting extending back to roughly 40,000 years ago. However, Greenland's ice cores only go back about 100,000 years, and earlier CO2 data are tainted by the presence of wind-borne carbonates from Canada in the ice. Long ice cores have come from 3 primary regions in Antarctica. The EPICA team collected the ice core with the longest record from the Dome Sea region of East Antarctica, dating back about 800,000 years, European project for ice coring in Antarctica. In 2004, the coring was finished in the ice at a depth of 3,270 meters. Another significant core, also from the East Antarctica-based Vostok station, was examined in the 1990s. Climate data from the Vostok ice core goes back approximately 400,000 years. The Byrd ice core record, which was dug to a depth of 2037 meters, represents West Antarctica. Stable isotope study has shown that the long-term temperature shifts in Antarctica are related to the natural climate variations brought on by the glacial and interglacial cycles that occurred throughout the Quaternary Ice Age. In comparison to the interglacial periods, which are warm for about 10,000 years, the frigid, glacial phases typically persist much longer. Our current interglacial has so far lasted for 11,700 years. Be aware that the amplitude of warm/cold oscillations increased around 400,000 years ago, according to the EPICA graphic. Along with significant fluctuations in temperature, these cycles also resulted in significant changes in sea level. During the last glacial maximum, sea level was approximately 120 m lower than it is today. These sea level changes were caused by variations in the total amount of ice on land, both in the Northern Hemisphere and in Antarctica. Importantly, the levels of carbon dioxide and other greenhouse gases closely follow variations in temperature. While the cyclical changes in the Earth's orbit, Milankovitch cycles, are responsible for the timing of these natural climatic variations, variations in greenhouse gas concentrations are crucial in exacerbating the initial temperature shifts. In other words, the amount of greenhouse gases in the atmosphere not only reacted to the orbitally generated temperature swings, but also increased the size of the temperature fluctuations compared to what they would have been without them. This provides strong support for the idea that altering the amount of greenhouse gases in the atmosphere, as we are now doing, will have an impact on the temperature of the planet. The East Antarctic ice sheet is less susceptible to climate change due to its bigger extent, higher elevation, and higher grounding level. It is even feasible that higher temperatures might result in a more positive mass balance and a thickening of the EAIS due to more snowfall in the interior. It is yet unknown how much Antarctica will contribute overall to the rise in sea level during the coming century, but this is a hotly debated topic. Please remember to like, share, and subscribe to our channel if you liked our video if you want to see more.